applications of this biogenic silica, protein coatings, and some natural mechano-responsive materials. So I will focus most in secretions, as I will talk about the velvet worm. I will also talk about some pattern surfaces that we can achieve with the biogenic silica and some other bioactive compounds. So some time ago, we started research trying to extract nanocellulose, as my colleague Melissa commented before, from the pineapple peels, because it was a problem for the country, because we produce a lot of pineapple and we have a lot of these residues, and when these residues are thrown away, a lot of mosquitoes are formed. The soil is not in the best state. So we started, if you see the microscopy here that I'm pointing out, we started to analyzing initially the raw material. Once we saw it in the microscope, we could see all these small, from here in this microscopy, looks like dots. They are well patterned, aligned all the shelf of the pineapple. And we started to analyze its composition. These small dots are finally rosettes of biogenic silica. They are well patterned and well formed by the plant. So how this biogenic silica is formed, for example, this is still a question. And we saw that this silica is aligned, for example, in one direction preferentially in the surface, giving mechanical strength in one direction, and is connected, if you see in this microscopy, but nanocrystalline cellulose. So we started, it was just not to analyze the material and to extract nanocellulose and to extract biogenic silica, but to look for a real application for these structures. One of the main advantages of the biogenic silica in the soil, we have different compounds. We have aluminosilicates, we have carbonates, but one of the main components that can help to hold water in the soil for crops, for example, is this biogenic silica. It has been studied that even 700% of the water, of the weight of the silica can be held by water. So it means that this biogenic silica that we collect from the pineapple peels could be suitable as a biofertilizer. Also, the biogenic silica is known for help to the mechanical strength of the plant. Sometimes even this silica in the plant makes the plant not so digestible for the insects. Also, the silicic acid itself helps to catalyze many biochemical processes in the plant that help to mechanical protection, for example. So it's known already in literature that the biogenic, that the silica helps as a fertilizer. Now we have a source that is not just biogenic silica, is a microstructure that is it has been already optimized by nature. So another, we start working in that application. Another application that we are working with is for crop protection. The biogenic silica itself has a these rosettes that we see here. They have a special morphology that has been known in many plants to have this pattern surface that helps to create a roughness that makes the insects not to adhere in the surface of the plant. So this biogenic silica cannot just be used as a biofertilizer, but also can be used for producing a natural coating for the plant, for avoiding the insects to be in the surface and to damage the plants. Sometimes It's known that many plants they have these patterns, and the insects can slip off from the surface. Another application we're working with is this biogenic silica that is optimized, this structured, has this roughness that goes in between 0.5 to 1.5 micrometers, that is known to be in cicada wings, for example, and that avoid bacterial adhesion or can be a killing contact surface in the cicada wings. It means that a surface that has this kind of these patterns on the surface can kill bacteria. So we can use this biogenic silica to make antimicrobial films, coatings from other materials for avoiding antimicrobial attachment or survival. So something really interesting that we learned in the process of analyzing the silica is this is a microstructure that is formed by several nanostructures. There are several levels of building. It's not built itself. We could find at least two more levels. We can find plates, and also nanoparticles. So these nanoparticles that form this Rosette structure are 150 nanometers. And as I learned in the process of developing extracting this with a mechanical process, this Rosette structure is not so tightly built. So with the mechanical processes, you can get nanosilica, and this can be used as a nanofertilizer, increasing the surface area and also improving the properties. So these are the examples related to biogenic silica. In the future work, we are doing this, using this silica rosette to produce smart coatings. Also, we want to understand how the cells can build this structure. It's not a precipitation. It has to be a controlled process to form it. Also, how these structures are formed during the developing of the plant until when the pineapple is reaped. So all these questions are still open and we are working on. Another example of what we do here is, for example, for protein coatings. The lacases are enzymes that are used are polyphenol oxidases. They are extracted or overexpressed in white fungi. And these enzymes, what they do is oxidate and form also polymers with polyphenols, with lignins. And they work normally in semi-dried state. So we thought about the enzyme not as for polymerize in the beginning the polyphenols. We looked at the enzyme and we saw that 60% of the sequence of the enzyme are amino acids that are hydrophobic. So this enzyme is set in nature to have a good addition or good interaction with hydrophobic surfaces as is good. So we thought, we test, in the beginning we thought maybe as is a polyphenol oxidase will oxidate the surface of a common plastic as polystyrene, and we treat the surface. We see these drops with the solution. After the drops and you dry, you see, for example, the polystyrene is hydrophobic, and after the treatment with lacase, it gets hydrophilic. In this enzyme forms a film that is irreversible, absorbed in hydrophobic surfaces in 1 minute. And it forms monolayers. What it means, monolayer of a protein, it means that I get one protein ball of 5 nanometers and I cannot form thick layers. It will get 5 nanometer layer on hydrophobic surfaces. And then, of course, we test if the enzyme was in the surface with techniques as tough seams. And we saw that it's a suitable treatment for replacing plasma, because as it's irreversible absorbed on the surface, we tested many solutions as bases and acids. We saw that the enzyme was still on the surface, and we use this as a replacement, for example, for treating polyester plates, the Petri dish, for helping to grow cells. So here I will show you an image where we see the control part, where the melanocytes, we test the addition of melanocytes, and we saw that in pristine polystyrene was almost no cells adhere. And in these cells, when we made this treatment with lacase, the cells preferentially adhere and really good. And also, we can treat the surface of a polymer quickly, and we also expose many functional groups that can help to attach another molecule. So we went further, and we immobilized antimicrobial peptides on the surface, because if we have a medical device as polystyrene, for example, normally these materials are not antimicrobial. So we wanted to make these materials in an easy way, in a way that a medium company can use this procedure and make its material more antimicrobial without a fancy equipment. And we first made a layer with the lacase, and where in the enzyme is still active. It doesn't mean that the enzyme absorbs in the surface of a material, of the polystyrene, and it's not active afterwards. It's active. So we put a peptide, as you see here in this sequence, where we take a known antimicrobial sequence, and we added dihydroxyphenylalanine as a coupling strategy. So the enzyme, if the peptide is close to the surface, the enzyme will be able to oxidize these catechol groups, and these catechol groups can link to different free amino groups on the surface. Of course, this is inspired by mussels. That it's known that these catechols in the sequence of the proteins make all these proteins adhere really well. And so we could form this interfactant layer in the surface and immobilize the peptide. We made some derivatization reactions that are selective for surfaces for this catechol hydroxyphenylalanine, and we saw that part of the peptide was reacted and was covalently attached. And we saw that that we could improve a lot the antimicrobial properties of the polymer surfaces. And so we went another step further, and as we know in biological tissues, we have electronic transport between proteins, between lipids and proteins in different environments. For example, here, bacteria, many people study the sequence of the peeling bacteria because it can transport fairly well electrons to do these biomolecular junctions. And so we went further, and as we had these protein coatings with lacase that adhere really well to hydrophobic surfaces, we could build layers with graphene oxide. So, and we developed a process, and we can really control. Here is a AFM image. This is here, what you see is a graphene oxide. And here is the protein. You see this is the phase image when we see the contrast where the graphene is flat and the protein. And we test how was the electronic conductivity. We have a tie-formed layer with a protein that has a lot of hydrophobic amino acids, that they have a lot of tryptophans, for example. They can make a good connection with the graphene. Of course, the graphene oxide is not conductive, it's graphene, so we could heat these layers to 200 degrees to reduce the graphene and next test the conductivity. And we saw that the conductivity of the layers of graphene was improved in contrast with the graphene alone. And also we saw that the conductivity, also that they were really stable. So we went another step further, and as we know nowadays, we have the lithium titanium oxide, anode and cathode materials. And these materials, and now everybody is working on producing nanoparticles and try to improve this material. But what happened with the lithium-based materials is they are not so well conductive. So you always, that you build an anode or a cathode or a battery, you need to add carbon black. And you need to add or graphene, and now everybody's using graphene oxide. And so what we thought was, okay, we know that these graphene lacquer layers and other proteins, because we use other systems, can improve to make this interface between a metal oxide and graphene. So we started testing testing building these layers and trying in anode material for batteries. And we could see that in this green curve here is when we cycle the battery without any binder, trying to improve the interface with the anode, between the titanium oxide and the graphene. And this is when we use optimized peptide. So we can say that maybe the peptides are not, we are studying that, are not the best electronic transport molecules, but they improve the interface and they tie together the graphene to these lithium basic materials, and they can help to improve the capacity of the battery. So we are, for the future work, we are still using these peptides or basic peptides for building these composite materials. We are controlling the thickness and distribution. We are trying to understand this electronic transport. This is something that is not trivial. Of course, we are trying to compare with from the beginning, we covalently attach or not the peptide. And we are studying all these different conduction paths. So as a last example that I will give you today about what we do here related to bio-inspired materials, I will switch a little bit. I work with a species that is from the rainforest here in Costa Rica. It's not only here, it's called Belgrave Arms. I will show you a video. It's less than 2 minutes because for you to know the species. This is a worm that is located normally in the rainforest, and that spills this slime for catching a prey. More the prey moves, stiffer this secretion gets. So this worm next comes and eats all the slime. And now, as it's harder, the insect cannot move anymore, and now the velvet worm comes and digests the insect. So there are great scientists here in Costa Rica that have studied the evolutionary part, or the ecology part of these species of the velvet worms. How this velvet worm is, storage this slime. This slime that spells on demand for catching a prey is stored in a reservoir. The reservoir has is part of the slime gland, where we have all these gland branches, where there are all the cells that produce all the components that forms the slime. And then all this produced material goes to this reservoir. And then the velvet worm has muscles surrounding this reservoir that it contracts for the slime come out and to catch the prey. So as you see here, this is a cross-section of the animal. Here you see the reservoir. The reservoir is big and comes from a big tube to a small tube. And this is how the slime gets like a accelerator or gets speed. So it looks like a syringe hose system. So the animal contracts, passes from a big reservoir to a small reservoir, gets speed, and is expelled. So part of the work we have been doing here was studying a little this material. Why this material? Because it's a unique material that is natural and is mechanoresponsive. So you take this slime and you leave it in a surface for 24 hours, and it stays liquid. It's like a droplet. But you touch it immediately in 10 seconds. It's harder. It hardens with the mechanical resistance of nylon. So in parallel, people from other countries and us, we publish about this material. So we wanted to understand how this material works, why this material dries so fast, and what is going on. Because it's important for molding on demand when you want to produce material with biodegradable materials that we extract from all these natural sources. So how we mold, because normally all proteins or many other carbohydrates degrade with temperature. So this animal expels this material, and it gets molded and get the shape of the animal in environmental temperature and in normal pressure. So how nature can do this without degrading the material? So we collected the expelled slime. Just a quick view how we collect. This is from another researcher from Costa Rica, from the National University. And we just stimulate the animal and collect. In this case, they collect in this device. We collect normally in glass. So one of the first things we saw is that the material is, when it's not mechanically stimulated, is white. So it means there is something changing the color, and after mechanical stimulation, it gets transparent. So under the normal microscope, the first thing we saw was that it has a lot of microparticles all spread all over the material. And we go further, and we went further, I will explain this soon, and we could see that this material, without any staining, it was full of these electron-dense micro and nanoparticles. So this cannot be a lipid, because normally if you want to see a lipid in the transmission electron microscope, you have to stain. And it was really electron-dense, and we saw that all these metals were preferentially stored inside these particles. Of course, these metals or these particles are inside a protein matrix. This protein matrix is formed by nanoglobules. But we were interested not in the protein matrix, that it has proteins, other lipids, carbohydrates. We were interested in why a material like this has already these microstructures in the slime, and why these microstructures disappear. And maybe we thought in that moment it could be correlated to this fast drying process. So first of all, when you have a material like this, you cannot do much, and you see these particles, because could be a drying artifact. You can have a liquid, and when it dries, salts precipitate, and it could be an artifact. Also could be an artifact of when the with the velvet worm spells. The velvet worm is in the earth, so it could have many dirt, soil. So initially we had to study both materials. How is the material outside the animal and inside the animal? Why outside? Because it could be like just a contamination, and inside to prove that. And the first thing we did was cryotem. We took the slime directly from the animal inside, and also the expelled one. Both are almost exactly the same. And we saw that this slime was formed by these electron-dense microparticles, and that even in using cryotem, we could clearly see them. So they are not an artifact because they were inside the animal and outside, and also in cryotem conditions that simulates the natural liquid environment. So as you see here, these are just some images that if you sleep with CO2 the animal, and the animal is relaxed, it won't expel. You could open and you could obtain the slime from inside the reservoir that is ready, that is full. You see it here, it's a white material. Of course, here, when you open an animal and you do a dissection, you have the hemolymph. This is like the blood of the animals. Part of what we did, not to confuse things, was to study the hemolymph of the animal taken from other parts. And I can tell you that the results I will show afterwards, it doesn't look anything as this insect blood. So part of what we had to do, also as we open an animal and see, is to do all the histology and how is this reservoir inside the animal. This is a cross-section of this reservoir. It's really interesting because it has two tubules, one inside the other, and each tubule goes different components. And here, normally in the muscles, is the hemolymph that is stored too. So what we saw, even in the expelled without movement of and also the one that we took from the reservoir, it was that we could form a pellet. This white material, this white color was due to these particles that we could, by a process. This paper has not been published yet, so I won't go a lot in details how we did that. By a process, we could collect these particles to understand what they were. So we did the normal analysis, infrared, TEM, EDX. We did a big study, even GCMS, many studies, and we could see that these particles were inorganic core with an organic shell. And then we could elucidate that these are just kind of vesicles or granules that the animal produce. As you see here we made a stem. Why stem? Because you can do EDX and TEM at the same time. Also, when you do TEM, you don't have to coat the sample with gold, because if a sample has phosphate, you will confuse the peaks with EDX. So we could see that the animal, what it has are all these particles that are sodium phosphates, basically. We see here, for example, this globule is based in phosphorus, in sodium, and also it has this carbon coating. And what these carbon coatings are a lipid and a protein. So our organic salts stored in these vesicles that are lipid proteins. So of course we went to prove that. It was not easy, because we went to the Talos in HDH. It's the best electron microscope available in the market, more sensitive one, because I always had the doubt that it could be like a kind of protein or so, and we could even not detect nitrogen. So yeah, inorganic particles. So we went and also could do a selector area diffraction. When you take the TEM, you select the area, as you see here in this corner, let's see here, and you do diffraction there. And with the diffraction there, you can calculate the d-spacing, and with the compounds you have, with the elements you have, match which species are forming these particles. So we could detect two different ones, carbonates. So in carbonates, we also track and quantify how much that it was real, that it was carbonates inside, and also phosphates. So we could do the mapping and also see the diffraction. And it was amazing, because we could even do diffraction in cryothermic conditions. So the crystals were there before even drying. So now we know that the animal storage all this slime, hydrogel, this protein and lipids, and also together with these vesicles. And these vesicles are part of the mechanoresponsiveness of the slime, because these vesicles are in the slime inside the animal and expel it, but they disappear when they are mechanical stimulus. So what we suggest that is happening is like with the mechanophores that is applied after the expelling, after the mechanical stimulus that the animal or the insect can do, is like to break these vesicles. All the phosphates and carbonates are released, and the slime is acidic. If you have acid with carbonate, you can even form CO2 to help to form a foam. You see here the pores. This is the material already expelled. You see a porous material formed. Also, we see that we don't find any more no sodium, no phosphate, not any other metal in particles, if not all over the material. So what we suggest is that the part of this gelation or fast gelation is the fast release of these phosphates. There are carbonates. There are common gelation agents. So, well, we proposed some equations about it. And now we are working, so we know the principle, and now we are working in the biomimetic of the material. We have, we are working with hydrogels that by the addition of these salts can gelate and can stiff or not. So we produce biomimetic vesicles and with the salts, and now we are added to the hydrogels, and we are testing this technology with normal syringes, to make technology that can be used for everybody in a simple way. So as I show you, I hope today, we wrote in one of our papers was there is truly plenty of room at the bottom of biodiversity. So I do not do all this alone. I thank all the agencies that have funded me during the years, and also the amazing students that we have at LANOTEC. There are only few here. I have worked with many, and sorry that I don't have the picture of you guys, but thanks a lot to all of them. And thanks to you.
Thank you, Dr. Corrales, for this impressive presentation and for showing us this huge amount of work that you've been doing in the last years, and especially in the bio-inspired materials, which is a hot topic nowadays. Well, now there is time for questions. If someone of you is willing to ask a question to Dr. Corrales, please raise your hand, and then I will introduce yourself, and you will be able to ask. Well, we have a question from Zeki Kandan. So please, Zeki.
Hi.
Hello. Hi.
Hello. It was a nice presentation. I'm Zeki Candan at Istanbul University from Turkey. It was a great presentation. Thank you, Mark, for your organizing. I have a question for you. How we can scale up the technology for industry, you know? Also I work on adhesive, you know, is perfect issue, is a kind of bioadhesive stuff or non-adhesive. How we can scale up this new technology, biomimetic technology for industry? Thanks.
Now, for example, you can clarify which kind of do you want to know about the biogenic silica or which of the topics? Sorry. Well, for example, in case of the biogenic silica, we already have escalated the process for forming these coatings. We are just dispersing really well the biogenic silica and really water super absorbent biopolymers that you can make a film easily by spraying or by just deep coating. And then, as it's a super absorbent biopolymer that you're using, when it dries, it just maintains, doesn't change the structure, the biggest microstructure, just form a layer on top of the silica, and you can get a coating. So it's interesting because the silica, you can disperse it with these super absorbent polymers, and you can form films. And normally, this biogenic silica is negatively charged, and it doesn't like to get together. It doesn't agglomerate. So if you put a polymer that it just can disperse well the silica, you can by spraying or by deep coating, you can make it, and drying. And for example, the velvet garment slime it has been we are developing some biomimetic proteins, hydrogels, using chitosan or using collagen. They're easy, and we are just producing by norm with the special molecules these vesicles that can keep the salts inside, and they are mechanoresponsive. So finally, the technology, how to apply, is not so complicated. It's more complicated how to produce sometimes the molecules we need for doing the biomimetic. Yes.
Thank you so much. That's great. Muchas gracias.
Gracias.
Okay. Thank you, Yendry, for this answer, and Zeki for the interesting question. Well, while we wait for more questions, I will take advantage of my position today, and I also have a question. So I would like to know if you could explain more in depth the formation mechanism of the biogenic silica rosette.
It's something that we are studying now, but I can tell you what is known and what is known in literature, how this biogenic silica is formed. And normally there are like 3 ways of being formed. One is that the plants, they have special components, glycans, in the cell wall, and they help to precipitate the silica in certain spaces that are preformed. A second way is we have these silafins. They are proteins that are special in nature for catalyzing the production of silicates or biogenic silica, and that do the catalysis. So when they have silicic acid, it forms these insoluble structures. And the third way, like say, is known in literature, is that is not known, is inside the cell. So also this, the cell has, the plant has these kind of vesicles when storage high concentration of, could storage high concentration of silicic acid that can also precipitate in special compartments. So, but today, unfortunately, we're working, I cannot tell you well what of these mechanisms is for biogenic silica, but we are working on that. Mm-hmm.
Okay, thank you. Thank you very much. And, well, in fact, what type of polymers are you testing for forming the pattern silica rosette films?
We can use common polymers. I use alignates, for example, pectin, for forming them. So actually, if somebody in the NANOCELIA network wants to make a collaboration with all of the polymers, the residues you already have developed, we can maybe talk afterwards and make a collaboration. Because yeah, it's like alignates, pectins, this kind of polymer works really well for forming these films, and these films can get, at least until now I can see, super hydrophobic, are super hydrophobic in some cases, and we are testing the antimicrobial properties.
All right, sure that there will be someone in the NANOCELIA network, or even not being part of the network, but that will be able to collaborate and to contribute to this work. I will leave your contact details in the video of the presentation, if you don't mind, and then you will be able, or people will be able to contact you for this purpose.
Mm-hmm. Okay, thanks a lot.
Well, and finally, I have another question, and I promise it is the last. I would like to ask you for the type of proteins forming the velvet worm slime vesicles. So this is the last example that you've been explaining, and I would like, which kind of proteins are forming this velvet?
It was interesting, how we did that. Of course, we have to do some proteomics. So part of what we did to understanding what kind of proteins were there, we extract all this slime gland of the animal. We do transcriptomics, so we have all the RNA sequences that we do bioinformatics, and we will know what are the proteins. And then we also, of course, extracted the vesicles, and we also sequence which proteins, and we match, we did transcriptomics and proteomics, and to see what are the proteins. But finally, what we saw, it was as a lipid with a special configuration. It's not a normal phospholipid. And also, we saw annexins. There are proteins that are known in nature for building with calcium, for example, for forming lipoproteins. So if you have calcium in this protein, it will bind to a lipid. So it's interesting how nature can form these vesicles. So we know the sequence, and we are using this as a base for the vesicles. Yes.
Yeah, sure. Thank you. Thank you very much for this answer. So, well, apparently we have no more questions, and it's 5 to 5, so we are close to the end of the webinar. I just would like to thank you again, your participation on behalf of the NANOCELIA network. Also, all of you for attending the webinar. And well, I wish you the best in your research for the next years and for your academic life. And I hope to see you all again in the next webinar that it will take place in 1 month. I think it's the 3rd of August. Okay. So thank you very much.
Thanks a lot to you guys and all the people.
And enjoy.
Ciao.
Bye-bye.